So I'm going to talk about ab initio calculations on iron alloys, and specifically, can mineral physics, or ab initio mineral physics, match seismology? So we've had this problem in the past when we're working on iron and iron alloys, looking particularly at shear wave velocities, that they're not matching the observation from seismology, and we have to be able to match it to have any credibility. So the outline of this talk is to briefly say why the core is interesting, and the first few talks have clearly shown that, and indeed you'll see quite a few similar slides. Then go through what ab initio calculations actually are, take away some of the black artness of it, and in particular simulating pressure and temperature, because we're trying to get to 360 GPa, so 3.5 million atmospheres, and maybe up to 6,000 Kelvin, so very high pressures and temperatures. And then I'll move on to the main part of the talk, which is what phases of iron and iron alloys can match the seismology. And we'll start off with pure iron phases, i.e. different structures of iron, then look at the effect of light elements, and finally the effect of nickel. So we've already seen this one, and it's the first of several that you'll see a few times. And this shows that iron, density of iron is much greater than that, or a little bit greater than that, observed for the core. So there's got to be some sort of light element or something lighter alloying with it to match the seismology. And this is a traditional view of the Earth. We have a core mainly of iron and nickel is often swept aside. It's very close to iron in the periodic table, so it's considered that the properties are going to be very similar, but I'll get onto that later. And then these light elements, which is the main thing that we've been talking about in the first few talks. The outer core is liquid, it's very runny, it's like water, it's got a viscosity of just a few millipascal seconds, and it's about 10% less dense than pure iron, with a temperature ranging, depending on where you are, from 4 to 6,000 Kelvin. And the inner core is solid with 3 to 4% less dense than pure iron. And we think that the inner core is crystallizing from the outer core and expelling these light elements, although clearly from the first few talks this isn't over the entire inner core boundary. So the outer core is very important because it's the source of the geodynamo, and it's during the crystallization that these light elements are expelled. There's preferential partitioning of light elements into the liquid, and once they come into the liquid, the buoyancy drives compositional convection, which helps the geodynamo. And the outer core is also very interesting for a number of reasons, because quite recently there's been a number of papers about stable stratification in the outer core. So at the core mantle boundary, there's this paper which says basically the topography of the core mantle boundary traps the fluid and gives some sort of stability to a stratified layer at the top. And then just a few weeks ago, there was this paper in Science about iron oxide, and it implied that structural changes in iron oxide at very high pressures and temperatures in the liquid, although the experiments were on the solid, but they made some extrapolations, would cause very different flow regimes in these stratified layers, and that, of course, would have a significant effect on the geodynamo. But only yesterday, which just shows how this is all contentious, Huang published a paper that ruled out oxygen altogether from the outer core. So, very interesting. Don't know what's going on, is the bottom line for that. And then we've seen these figures already. So this is at the inner core boundary, where we've got this possible translation of grains across, and we've got crystallizing on one side, melting on the other. We've heard about that. And then also this year, this is a geodynamo model where Gubbins and his folk have said that the heterogeneities in heat flow in the core are such that you could get heating up of the inner core above its melting temperature without any cause or need for these sorts of models, just purely on heterogeneities in heat flow models. So then we get to the inner core proper. So there is this observed layering. So this is all the inner core. We have an outer inner core and an inner core. There's significant anisotropy, and the hemispherical variations that are observed in the seismology. And then I mention here melting of the inner core, which I'll come back to later. I don't mean at the boundaries, but possibly within the inner core, in a sort of plum pudding type model, you might get little pockets of melt. And this has got something to do with the mismatch between mineral physics and seismology on the shear wave velocities. The inner core is very distinct, possibly a different phase, but it doesn't have to be a different phase because the anisotropy of the hexagonal phase of iron changes with temperature, such that the higher the temperature, it almost reverses in its sense. So it doesn't have to be a different phase, but it might be. And then this idea of preferred orientation over time leading to some sort of texture, which possibly has something to do with the layering. So finding out about the core with ab initio calculations. Seismology is the observation. That's what we have. That's what we have to match. And from seismology, you get all the elastic properties, and in particular from VP and VS, you can relate those back to the elastic constants. So we can calculate these properties on crystalline iron and iron alloys, and then go through a range of compositions and wait until we find one that matches the seismology and then go, oh, that's the one because we've matched the seismology. If only it was so easy. What does computational mineral physics involve, and in particular ab initio calculations? We're talking about atomistic scale modelling. So we're talking about setting up boxes of atoms in a cell, and all the atoms are sitting there at some predefined crystalline structure. And what you calculate is the bonding between the atoms. And you calculate this ab initio, i.e. you calculate quantum mechanically the electronic interactions in the whole system. Okay? In principle, this should be done by solving Schrödinger's equation. But there's a problem with Schrödinger's equation, far beyond me, for anything more than one electron. So there are these little theoretical tricks you can use with a bunch of acronyms that get you past the problem of calculating quantum mechanically the energetics of a multi-component system with many electrons in it. So what we're doing is we're using a particular code with a bunch of nice little bits of theory that get us past this one electron problem. Numerically solve Schrödinger's equation. Now the key thing is there's no parameterization, so there's no fitting to experimental data, nothing of that sort. It's all straight from first principles, all from knowing where you are in the periodic table. That's all you really need. And you set up your box of atoms in some particular way, and with these methods you can predict a range of properties of interest, and in particular we're talking about seismic wave velocities, but you can also calculate and free energies, which I'll get onto in a minute. Sorry, that's volume, seismic velocities, free energies, but also you can calculate pretty much whatever you want. And this is essentially what you're doing. The stable structure is the one with the lowest energy. So if your atoms are too far apart, there's an attractive force pulling them back together. If they're too close, then there's a repulsive force bringing them back together. And the stable structure is the one where the atoms are happiest, they're at their lowest energy, and they have no forces acting on them. Now, to simulate pressure, because we're getting to these very high pressures, we choose a volume. Okay, so we've got our simulation box of atoms in some particular volume. We vary the positions of the atoms and the cell dimensions to produce that minimum energy structure, that stable structure. We check this because we look at the forces on the atoms, all calculated, look at the forces on the atoms, and when they are zero, we say the structure is happy, it's at its minimum energy. Calculate the energy of the system, ab initio, change the volume, repeat the process. And you end up with something like this, an energy versus volume curve, which gives you an awful lot of information about your system through its derivatives. And we fit that to an equation of state, like, for example, the Birch-Moynihan equation, and you get something like this, pressure versus volume. The stars are the experiment, and the line is the calculation, and particularly at very high pressures it fits pretty much perfectly. There's a little bit of a deviation at low pressures, but that's well known and to do with magnetic structures, which we've since sorted out. But the main thing is it fits very nicely with the high pressure, the core region. Now, temperature. Temperature is a bit more of a tricky issue. Okay, it's computationally much more demanding than modelling pressure. And there are two ways of doing this. One is lattice dynamics and the other is molecular dynamics. Lattice dynamics is slower than, is more intensive than just looking at pressures, but it's much quicker than working with molecular dynamics. But the problem with lattice dynamics is it doesn't work so well for very high temperatures. So we have to have a balance between economy and wanting to get to, let's face it, the inner core is very close to its melting temperature. So we use a combination of both depending on the properties that we're interested in. So let's consider lattice dynamics, a quick foray into ab initio calculations. Above 0 Kelvin, in any crystalline structure, your atoms are just wobbling around, and the higher the temperature, the more they wobble. And they wobble in 3 dimensions, in a sort of thermal ellipsoid, and could be spherical or it could be ellipsoidal, depending on anisotropy of the thermal motion. And you can describe this very complex 3-dimensional motion of a whole number of atoms by a series of quite simple waves. And it's a bit similar to this sort of a thing. You have a complex motion, shown by the top trace, and this can be devolved into a series of very simple sine waves, each with a frequency called a vibrational frequency or a phonon, omega I, and some wavelength. And it's that frequency which is the key thing which we calculate, because that frequency then goes in to relations like this, and there are very similar relations for a whole bunch of properties, and they're all dependent on the frequency. Everything else is a constant, or you put in your desired temperature post-processing, but the main thing is once you've calculated your frequencies, that's the end of the calculation, you can then work out the property that you want. Okay? Now, molecular dynamics, so the shortcoming of that is that when you get to very high temperatures, it doesn't work so well, so you need to go on to something called molecular dynamics, and this is where your wriggledy-jiggledy motion of all your atoms in your crystal are described by exactly that. Now, with any luck, this will work as a... So here we have, I think this is MgO, but we have on this side, we have a solid, and on this side we have a liquid. And this is a 2-phase simulation box, so we're actually at the melting temperature of this particular MgO material. And we're modelling, whether it can be modelling the liquid or modelling the solid, but we're modelling the motions of those atoms by calculating at any particular step in the process. So say this was a configuration, so that might be step 1. And then if I can make this again work properly, that will be step 2, that would be step 3. And at each step, you calculate the energetics ab initio with this quantum mechanical theory. And that gives you the forces on each of the atoms. And depending on what the forces are, via Newton's laws, you move the atom according to what those forces are telling you to move them. And you carry on like this for a long time. And then you get an output which looks a bit like this. Now, the y-axis could be anything. In this case, it's temperature, but it might be atomic position, it might be stress, and they all look like this, some sort of wriggledy-jiggledy thing about some average, which is hopefully a straight line. Okay? And so this is simulation time at the bottom. And if you do it for long enough, you end up with something that's very well converged in its wriggledy-jigglediness, and you can take the time average of that property. Now, in this case, it's temperature, but as I said, it could be anything, and in particular, stress for the calculation of elastic constants. So let's get back to the problem. So the problem is we want to know what's causing inner core complexity. Okay? We need to know what the composition of the core is. We know it's iron with some other bits and bobs in. So the first approximation, we look at iron in its pure form at core conditions. Can we match seismic wave velocities? If we can't, we then say, oh, well, what should we do now? Let's add some light elements, see if we can match the wave velocities, and then we look at the effect of nickel. So this is the phase diagram of iron. So the stuff that you hold in your hand is a body-centered cubic phase, so atoms at the corners of a cube and one in the middle. Heat it up, and it goes to a face-centered cubic phase, FCC, atoms at the corners and one on each face, and you squash it, and it goes to this hexagonal layered hexagonal structure. And this is quite an old diagram, but the problem has always been, here we are in the, roughly, somewhere around here, in the inner core. What is the structure? What kind of phase transitions are occurring or have occurred to this point in the inner core? And there's been a lot of work, people trying to determine this. So, one of the things that we did a few years ago was to look at the free energy. Okay, so the free energy of the stable structure has to be the lowest compared to any other candidate structure. And we did this for pure iron at core densities and temperatures, and found that the free energy of the hexagonal phase was lower than that of the other two candidate phases. However, you have to be very careful because the energy difference between the hexagonal phase and both the body-centered cubic and face-centered cubic is very small, orders of tens of millieV. Okay, we know that means that it won't take much for those phases to change if there's a more favourable condition, for example, light elements. So we have to think about that. But we're just for the moment talking about the pure phase. And then experimentally, this has now been confirmed. And this is the diamond anvil experiments by Totino et al. Last year. And he's now shown that there are no phase transitions, further phase transitions from the low pressure region. And by the time you get to the core, you're still in HCP. So that's okay, that all works, that all fits together. So what about the seismic wave velocities? We've got to calculate the seismic wave velocities, and they're a function of the elastic constants. How do you calculate the elastic constants? You set up your box. This is a simple case of a cube. There are similar cases for the HCP phase. And you basically push and pull it in different directions according to some deformation matrix. Calculate, so you know what the strain is because you've put in the strain. Calculate the stresses, so we get one of those wiggly diagrams with stress difference on it as a function of simulation time. And in this way, work out the elastic constants. And there are 3 for the cubic phases and 5 for the hexagonal phases. And we do this with molecular dynamics, that's the high temperature method, at the conditions of pressure and temperature for the Earth's inner core. And we take a step back and we say, well, we must, of course, compare this with experiments, because if we can't get the right numbers, then there's no hope for core conditions. And these are experiments of Jimmy Badrow, which are the straight lines for pure iron and iron silicide, which I've just extrapolated with dashed lines. And these are the various symbols are different flavours of the simulation. And we can see that they agree remarkably well. So we're happy with that. But can we match seismology? And the answer is, with pure iron, not yet. And the problem is with the shear wave velocity. So with pure iron, the shear wave velocities are greater than those that are observed by 10 to 30%, depending on which of these numbers you choose. So there's a problem. We cannot match seismology with pure iron. And at the time of writing this, we decided to come up with a model of an inner core that had some melt pockets in it. I'm not talking about the melting at the inner core boundary. I'm talking about within the inner core. Some melt pockets such that the observed shear wave velocity would be reduced, and that was causing the difference between our sort of perfect solid and the observation, which might have also been passing through some fluid. And to account for the difference, the amount of melt that you would need ranged from 8 to 25%, so a lot, something fairly significant. But we're not stopped yet because we've got light elements to consider. So what happens when you add light elements? Now, the phase diagram of pure iron is this grey line here, and these are experiments that show that if you add light elements to pure iron, it pushes the phase boundaries to the right in favour of the body-centred cubic phase. Calculations also show that if you add light elements like silicon and indeed since sulfur, oxygen, carbon, they favour being in a body-centred cubic structure. It's called the cesium chloride structure because it's got different atoms in it, but the topology of the atoms is exactly the same. So they like being in the cubic structure. So there's a lot to be said for thinking, I wonder if we take light elements, we put them in the body-centred structure, is that going to change the structure of the iron alloy in the inner core and make it body-centered cubic, because the free energy difference is very, very small. It shouldn't take much. However, let's just see what we can do with the seismic wave velocities. So you add these light elements to pure iron, calculate the seismic wave velocities, and the problem gets even worse for the shear wave velocity. In fact, the difference is up to 50%, depending on, again, on which numbers you choose. But 10 to 50%, okay, for adding light elements. So that's gone the wrong way. So light elements do not help us with the shear wave velocities. What's more, the amount of melt that would give in the inner core, if you went along that model, would be significantly more than 25%. So it's all starting to look a bit unlikely. So possible explanations for the difference or the mismatch between seismology and this mineral physics calculations: partial melt, which I've already mentioned, anelasticity, lateral density and homogeneities, defects in iron, or compositions that we've never looked at. But there's another thing which is related to composition, is nickel. And as I said before, nickel is often overlooked on the grounds that it's so close to iron in the periodic table, but it's got some interesting properties when you add it to iron. So this is the phase diagram of iron. This is quite an old version of it. And you add nickel, and it pushes that phase boundary the other way, the opposite way to light elements, i.e., it favours the hexagonal phase and the face-centred cubic phase when you start to add nickel. And this was quite an interesting little idea. If you imagine crystallising an outer core, and as you cool, depending on the amount of nickel that you have in your system, you might cool a hexagonal phase, or you might cool, in this case, a face-centred cubic phase. Or, if you were just at the right place and you waited long enough, you might cool two phases, a hexagonal and a face-centred cubic phase. And so the conclusion of this paper is that you could somehow describe this inner core, outer inner core, by phase changes related to the composition of nickel. And the only problem we have with that is that the percentage nickel required to get the nickel with low, iron with a low amount of nickel in it is in the hexagonal phase, and it requires about 40% nickel to go into the face-centred cubic phase, which is a bit too much. Anyway, it's a nice idea nonetheless. But what about the seismic wave velocities? And this is very recent, within the last few, in fact it's not even submitted, let alone published. So these are the VP and VS on hexagonal iron with nickel, okay? VS, VP, and so on. But the key figure is here, so this is the percentage variation. So what we're looking at for is at least roughly 10% difference in shear wave velocity. And we find that for pure iron, it starts up here, and as you add nickel, you're getting a significant reduction in the shear wave velocity. So by the time you get to 25%, you've reached the magic 10% required to match seismology. Now, 25% is probably unrealistically high, but even with 10 to 15%, you're still on the 6 or 7% reduction in shear wave velocity, which is going a long way to explaining the difference between the mineral physics and the seismology. Now, there's a caveat to this because these are cold. These have not yet been done with molecular dynamics, and that is something that we're actually doing at present. So, in summary, we have what we think is a very simple explanation. The observed shear wave velocities are at least 10% lower than those of pure iron, and even worse for iron with light elements in. But we don't need a complicated assortment of explanations. Nickel has an unexpectedly large effect on the velocities of the hexagonal close-packed phase, and depending on the concentration of nickel in the core, we show that the observed velocities in the inner core are consistent with an iron-nickel alloy in the HCP structure with a very low proportion of light element. Thank you.